Okay, we've been talking about how cells make and use energy, and this is just a little bit of a recap from last time. But we started talking about the laws of thermodynamics. The first law of thermodynamics, circled here now in purple, is that energy can be neither created nor destroyed. And all that means for us is that what goes into a chemical reaction's gotta come out. If you start off with a molecule that has 6 carbons here, C6H12O6, you need to end up with 6 carbons on the other side. You can't have just one. So we had to add a little 6 here to balance the equation, which then changed the oxygens and the hydrogens. We had 12 hydrogens over here. We need to have 12 coming out. 6 plus 12, 18 oxygens going in. We have to have 12 plus 6 coming out. So that's all that means for us. And the second law of thermodynamics is basically what's called the law of entropy. And it basically states that everything is headed towards greater disorder in the universe. And for us, what that means is that a concentration gradient isn't stable, and that energy is released when a gradient has been equalized. And you wrote this sentence back up a little farther, and I had you circle it and put stars and swirlies all over it because we're gonna need that later on. So please make sure you've done that. So in our study of how cells make energy, we need to talk about a few things first. The types of chemical reactions that are involved, enzymes, some other players that are involved with helping your cells make ATP. So just to start off, I'm going to write that equation up here that we had back here. This one up here. I'm going to write that again for hoots and giggles. C6H12O6 eventually has to combine with 6 oxygen molecules to produce 6 CO2 molecules plus 6 water molecules right there. A lot of you may have seen this overall chemical reaction before. It is the overall chemical reaction. I'm abbreviating chemical with chem. I'm abbreviating the word reaction with Rxn. This is the overall chemical reaction for what we call aerobic cellular respiration. Aerobic cellular respiration. It's how our cells make energy. So sometimes you will see something like this written here, like plus ATP. We can write it that way. Sometimes you'll see it that way. It's not really an accurate way to write the actual chemical reaction, but that's okay for now. All right, and I just want to remind you all that this is glucose over here, C6H. Oh, did I put a 12 there? Darn it, that is wrong. Let's see, 6H12O6. Got a little ahead of myself there, didn't I? All right, glucose has carbon, hydrogen to oxygen in a 1:2:1 ratio. So we've got a 6-12-6 there. We know that that is a simple sugar. Let's go back to green here. But basically we breathe in oxygen, don't we? And we spit out carbon dioxide. This is how our cells make energy. Our cells need to break down a sugar like glucose, combine it eventually with oxygen to make ATP, and in the process we spit out some CO2 and some water. So let me get rid of those little arrows right there. Okay, so we will be looking at this, how this process happens, this process of aerobic cellular respiration. And I want to point out a couple of things about this chemical reaction. First, I want to show you and point out to you that all 6 of these carbons here get converted to CO2. Like I am the only place over here in the products. These are the products over here. These are the reactants over here. Let me get rid of the word glucose, that'll help. Reactants. Misspelled that. The only place over in the reactants on the left-hand side where I see carbon is right here. Right? And the only place that I see carbons in the product end are right here in CO2. So I am absolutely 100% convinced that all of the carbon in glucose gets converted to CO2 in this process. So there we go. We can connect those two. Now I'm looking over here going, well, let's connect the other two things, this reactant to this product, right there. That oxygen eventually combines with it looks like hydrogen that came from here in glucose and produce water in the process. You all know that we breathe in oxygen, we spit out CO2, but we also put out a lot of water as well. Let's get rid of that right there. And I want to point out a few more things too, that this process here where all the carbon in glucose gets converted to CO2, this happens first. This whole thing doesn't happen all at once. This part happens first. And over here, oxygen becoming water happens last. Okay, so another point about aerobic cellular respiration is that this whole thing doesn't happen all at once. So, cellular respiration, I'm just going to write cellular resp, doesn't happen all at once. In fact, this whole chemical reaction here happens in a series of chemical reactions, many chemical reactions. I can't remember exactly how many. I counted them all up one time, and I want to say it happens in, let's say, like 16 different chemical reactions. So this is just, oops, there we go. This is an overall chemical reaction. And it's made up of, I don't know, more than 16 different chemical reactions. And this over here, these reactants, that's the starting point. These products over here, that's the finishing point. And it's kind of like this. Like, let's say, I'm going to give you an analogy here. Let's get a different color. Let's do blue. Let's say you and your cousin are going to take a cross-country trip. There we go. Here's the U.S. I even put in the Baja California over here. So Maine's up here. Let's see. Oh, I want to draw the Cape. Let's give me a little space there. Let's put Massachusetts right in here, and there's the Cape. Ooh, I'll even put a little dot there for Martha's Vineyard. There we go. All right. So let's say, let's go with brown. You're starting here in Holyoke, and you're going to take this big cross-country trip. Probably not this summer because, well, who knows, we might all be in quarantine still or in lockdown. Let's say summer 2021. You and your cousin are going to take a cross-country trip, and you're starting in Holyoke, but your cousin doesn't live in Holyoke. Let's say your cousin lives in Baltimore. You travel to Baltimore, and you pick up your cousin. Then you're like, oh, wow, Baltimore is really close to DC. Let's, cross the Potomac and we'll go over to DC. Or I don't know which side of the Potomac Washington, D.C. is on. But, you go to the Air and Space Museum. You go to the National Gallery of Art. You go to the Natural Science Museum there. Really cool stuff. And then you start your trip. You decide, okay, you're going to drive all the way down to Disney World. So you go down to Orlando, Florida, somewhere down here. And you go to Harry Potter World. I would love to go to Harry Potter World and the new Star Wars installation there. And you drive the Millennium Falcon, have a great time. Then you decide it's time to leave. You're going to go to New Orleans. So you'll travel over here to New Orleans. You're going to listen to some awesome jazz. You're going to eat some amazing food, drink some really great coffee there. Have a great time for, a week. Then you're going to drive across Texas. I've done that before. It can be really boring. But you end up in West Texas at Big Bend National Park. You go to Big Bend National Park and you see all these really interesting rocks. I don't know. I've actually never been to Big Bend. But you're so impressed with the Southwest that you drive across what would be Arizona on into New Mexico, and New Mexico, then Arizona, and you decide you're going to go over to the Grand Canyon. Right about there. Grand Canyon, really, really amazing. And then you and your cousin drive, I don't know, maybe you go over to San Diego. You drive Highway 1 all the way up here to Portland, Oregon. You enjoy Portlandia for a while. You decide to visit Yellowstone National Park up here. And then you decide, okay, we really need to be getting back because it's August now. But who wants to drive all the way from, Montana? Well, you're not going to want to drive from Montana back to Holyoke in a day. So you stop off in Chicago because you have an aunt and uncle there, or other cousins there, and you're visiting them in Chicago, and you go to a Cubs game. Again, this is going to be summer 2021 when all this pandemic stuff is hopefully behind us. And you hang out there, and then you drive across, Ohio, Pennsylvania, and you end up in Cooperstown, New York. All right, and if we were in person, I'd be like, okay, what's in Cooperstown, New York? And somebody who's a baseball fan goes, Baseball Hall of Fame. And I'm like, yeah, you go and you visit the Bloody Sock and all that stuff. And Cooperstown is really lovely. It's close to Ithaca. There are beautiful gorges that are around. There's a lot of great hiking. It's a really nice place to be. And you decide to spend the rest of the summer there. So basically, what your trip was is that you started in Holyoke, but you ended up in Cooperstown. So you started in Holyoke, and you went all this way around and saw all this cool stuff, and you ended up in Cooperstown. And in fall of 2021, maybe you're taking a class at HCC again, and you're telling some of your classmates all about your trip, and they're like, wait a minute, you started in Holyoke, went all this way, and you ended up in Cooperstown, and it took you like 2 months to do this? Like, why didn't you just drive from Holyoke to Cooperstown? That's like a 3-hour drive. You'd save yourself all this time. And you're like, but I got this really fun trip. All by taking the long way around, I got a lot of fun out of it. Going to all these cool different places. You got a fun ride. It was great. It was inspiring. It was just, made your 20s, if you're in your 20s. And what I'm telling you here is that this chemical reaction right here doesn't happen all at once. I mean, sure, I could go over to Frost Building and put a bunch of pure glucose into one of those ceramic dishes, put it on a Bunsen burner, and I can get some of that glucose to combine with oxygen that's in the air, and we'll get some carbon dioxide and water out of it. But we won't get any ATP. So taking the shortcut going from Holyoke directly to Cooperstown is like going the short way, but you don't get any fun out of it. If the cell did that with breaking down glucose, it wouldn't get ATP out of it. Instead, the cell breaks down this process here into a bunch of shorter trips, just like you took with your cousin. Here. This here would represent one small chemical reaction. Then this line here, this little trip here from, what was that, Maryland to DC, would be another chemical reaction. And by taking the long way around, the cell starts with glucose over here, takes the long way around, does a whole bunch of individual chemical reactions, and because it took the long way around, the cell gets ATP out of it. This, again, does not happen all at once. Doesn't happen at once. Instead, to get from a starting point of glucose and oxygen, the cell does a series of individual chemical reactions, like you and your cousin on your road trip, taking a whole bunch of small little trips that add up to a big one. Takes more time, but you got a lot of fun out of it. This takes more time, but the cell gets ATP out of it. So that's a little analogy that I've used before that people have found helpful in the past. I hope you have found it helpful as well. All of these individual side trips represent a smaller chemical reaction that help the cell to get from C6H12O6 and 6 oxygens to 6 CO2 molecules and 6 water molecules. This doesn't happen all at once. If the cell did this all at once, it wouldn't get any fun out of it, and the cell's idea of fun is ATP. The only way you get ATP out of this is if it's broken down into a whole bunch of smaller chemical reactions. So we got to talk about some chemical reactions. Next heading, different types of chemical reactions. Alrighty. So let's take a look at this. Let's write, instead of C6H12O6 or one of those individual chemical reactions, I just want to write a generic chemical reaction for us all. So let's say substance A, and it could be anything. I'm just making this up. I'm just using a letter as a placeholder here. Let's say substance A chemically reacts with substance B to form substances C and D. So these over here are called the reactants. I've mentioned these before, but let's just be clear again. So over on the left, we have substance A reacting with substance B. They're the reactants. And this arrow here means a chemical reaction occurs. And over here on the right, C and D, these are our products. Right here. Products. Now, chemists and physicists can actually look at a set of reactants and assign a certain amount of energy to them. So we can assign, well, scientists can, I can't personally, but chemists and physicists can assign a certain amount of energy to reactants and products. And we can actually put this on a graph. So for example, we draw a graph right here. Let's see. So for this chemical reaction, A plus B going to C plus D. Let's see, I'll put energy on the y-axis. Time will have to be on the x. There we go. And let's say that, and I'm just making up this number scale here. Let's say that scientists have determined that the reactants A and B have an energy of 1, 2, 3, 4, 5, 6. There we go. 6. And let's say that they've determined that the amount of energy that the products C and D have is down here at a 2. So I'll put them down here. Let's connect the dots here. And A and B are starting up there at a 6, C and D end up at a 2, and we just connected these two levels here. Does this chemical reaction look like it's going to happen easily or hard? Does this look easy to go from A and B down to C plus D? Easy or hard? If you said easy, ding, 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 you are correct, because this thing looks like we're going downhill. And we all know it's pretty darn easy to go hill, or at least it's easier to go downhill than uphill. We give this kind of chemical reaction a name. We call this an exergonic reaction. Exer means to come out of, and gonic refers to energy, I guess, and then reaction, you know what the word reaction is. And here's what it is. Can you see that there is a difference between 6 and 2 here? A difference of, what, 4 energy units right there? So where did that energy go? What happened? Well, it came out of the chemical reaction. This exergonic reaction actually releases energy, and this one in particular is releasing 4 energy units. So if you look back up here under chemical reaction, substance A plus B going to C plus D. If its energy graph looks like this one down here that we just drew, I would be like, all right, well, if these ones are starting at a 6, the reactants are starting at a 6, and the products are starting at finish off at a level 2, that means 4 energy units came out of it. I would probably just write it this way. I would draw a small arrow coming out of the main arrow, and I know you've seen this before in class, and I would just write the word energy. Energy comes out of that reaction. An exergonic reaction releases energy. And they release energy because A and B, the reactants, have more energy than C and D, the products. So let's add a little more to this. Exergonic reactions release energy because the reactants have more energy than, hit something, have more energy than the products. You've seen something like this before. We have talked about an example of an exergonic reaction a lot in this class. And a real life example of this, not just, some generic A plus B reacting with substance A reacting with substance B to form product C plus D. You have seen ATP with its 3 phosphate groups lose that initial phosphate group because that's a high energy phosphate bond there, and ending up with a DP. Like this, and this releases energy. That's how the ATP molecule is used by the cell. It is an exergonic reaction. Right there. This releases energy. So let's take another look. Let's go back to blue. Let's look at a graph a different way. Okay, if we still have substance A reacting with substance B to form products C and D, draw our little energy graph. We'll have time down here on the x-axis and energy over here on the y-axis. 1, 2, 3, 4, 5, 6, 7, 8. All right, and let's say this time, though, that chemists have determined that substance A and B start off down here at a 2. And it's substance C and D that finish off on a 6. We'll connect the dots. And I'll ask you again, does this chemical reaction look like it's going to be easy or hard? And if you said hard, you're right, because look, it's going uphill. It's going to take some energy to go uphill. You know that. You know, it takes way more energy to go uphill than downhill. It doesn't take any energy to go downhill, but it takes energy to go uphill, like that. And if you're wondering how much energy units it's going to take to go up this particular hill, I'm looking at this going, well, that's the difference between 6 and 2, so that's 4 energy units, right? This thing's not going to be releasing energy. In fact, 4 energy units has to go into this chemical reaction to make it happen. So up here, I would draw a little arrow going in to the main arrow and write the word energy. This is not an exergonic reaction that releases energy. This is the opposite. Energy is required to make this go. So this isn't called an exergonic. This is called an endergonic reaction. And endergonic reactions require the input of energy. So they require the input of energy in order for them to happen, in order for them to occur. And this time, that's because they're finishing up, the products have more energy than the reactants. Or let's say the reactants have less energy than the products. Because the reactants have less energy. Let's fix that. Have less energy than the products. And we've seen something like this before in this class also. We have seen a real-life chemical reaction that looks like this. It looks like a little phosphate group getting back together with ADP. And what do those form? They form ATP again. But energy has to go into this to make that happen. And this is an example of an endergonic reaction. Energy has to go into this reaction in order to get the phosphate group back together with ADP to form ATP all over again. That is an endergonic reaction. Okay, so on the trip, I'm going to scroll back up here. On our road trip, or let's call it the cells road trip here, of getting from C6H12O6 and 6O2 over here to making CO2 and water and ATP, some of those chemical reactions are going to be exergonic So some of these side trips are going to take energy and some are going to be an easier ride. Some will release energy. There you go. But all of these, all of these little side trips here, at least all of these little chemical reactions in the cell to get from C6H12O6 and oxygen over here to CO2 and water and ATP, are going to require a class of molecules called enzymes. Enzymes. Here we go. Enzymes are required. All right. We briefly talked about enzymes back when we were talking about proteins, because enzymes are proteins. Remember when we were talking about proteins going, okay, some proteins are enzymes. Some proteins are transport proteins. Some proteins are antibodies. Some proteins are muscle, that sort of thing. So, but enzymes are all proteins, but not all proteins are enzymes. So enzymes are proteins. And specifically, they are proteins that catalyze chemical reactions in the cell. And this word catalyze here, we've talked about this a little bit. Catalyze means to speed up. But more than that, it's really to speed up and make happen in the first place. Because the deal with chemical reactions that have an enzyme that works on them, enzymes don't just speed up those chemical reactions, it makes them happen in the first place. And if that enzyme's not there, that chemical reaction is going to happen so slowly, it's probably never going to happen. So catalyze. To catalyze means to speed up and make happen. Back to green here. Proteins that catalyze chemical reactions in the cell. Okay, so enzymes are proteins that catalyze chemical reactions in the cell, but the deal is they are not one of the reactants and they are not one of the products. So we need to add to our definition here and say that enzymes are proteins that catalyze chemical reactions in the cell without being used up or changed in any way. So without being used up or changed in any way. We say they go in the same and they come out the same. They go in the same and come out the same. There we go. Getting tired of this green. Let's get a different color going. How about orange? There we are. Alrighty. If an enzyme works on a chemical reaction, like, okay, let's get back to our generic, substance A reacts with substance B to form product C plus D, oftentimes you will see written in teeny tiny lettering the name of the enzyme above the reaction arrow. Like, I'll just write some generic enzyme, we'll call it enzyme Q. That is a Q right there. And the name of it will be written in much smaller font above the arrow. That's very common to see that. Shall I show you that? Okay, so enzymes are proteins that catalyze chemical reactions in the cell without being used up or changed in any way. We got to talk about how they do that. So how do enzymes work? How do enzymes work? There we go. To talk about that, I want to go back to one of these little energy graphs here, like this. Or let's just draw a new one. All right. And let's say, how did I do this? 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, let's just make this a little higher. Let's say 1, 2, 3, 4, 5, 6. Let's start. Let's say that scientists have determined that the reactants A and B start off at a level 6. And let's say we finish off, the products are at, have 2 energy units. I've got time over here. There we go. All right, now I know we did this before and connected the dots like that, but guess what? I kind of lied to you. It doesn't really look like this, at least not for chemical reactions that have an enzyme working on them. Here we go. Not gonna look like that. The graph actually looks more like this. Like that. Now before you're all, what the heck is that supposed to be? I want us to look at this. Think about if you were riding your bike over this path here, starting in A plus B, going up, and then going way the heck down there, like that. And what's this level up to? 7, 8, 9, 10. Okay, 10. What this means is that you had to climb up this hill before you got an even steeper downhill, right? Because we didn't go like this. We didn't do that, right? That would have been easier, but that's not the way real life is. Sometimes there's a hill in your way and you're like, man, why do I have to climb uphill on my bike if I'm just going down to the same level here? Why can't I just go this way? Well, because nature put a hill there. Because that's the way it is. Seems like a crappy answer, but this is the way it works in the cell. What this means is that you got to go over this hump here that's this high in order for this reaction to go. Even though this chemical reaction looks like it should happen easily, it doesn't, because it's got to go over this hurdle here first. And this hurdle here, the difference between where we start at level 6 and up to a 10, this is the amount of energy that has to go into a chemical reaction just to get it started. And that's called the energy of activation, or capital E with the subscript capital A. We'll call it E sub A, like that. It's the energy of activation. It is the energy that is required by a chemical reaction just to get it started. So the energy required just to get a chemical reaction started in the first place. Even though this looks like it should happen by itself, even though this is an overall exergonic chemical reaction, it's still got this hump to go over. It's kind of like this. If you've ever heard the saying, you need to spend money to make money. Yeah, like if you want to win the lottery, you still got to spend a couple bucks on the ticket, right? This is the same sort of thing here. It takes some energy to get this chemical reaction going in the first place, even though they're overall gonna release energy. The energy of activation, right there. All right, so now you know what the energy of activation is. I want to point out that this is what it looks like. Why did I do that? Don't do that. There we go. This is without. W/O stands for without, because I can't fit it in here otherwise. So this is without an enzyme. things are going to look a little different with an enzyme present. When there is an enzyme present, this graph is going to look like this. Like that. This is with an enzyme. So think about what the presence of that enzyme did to the energy of activation. Did the energy of activation increase, or did it get smaller? The energy of activation got smaller with the presence of an enzyme. So how do enzymes work? How do enzymes work? They work by lowering the energy of activation. Enzymes work by lowering the energy of activation. I'm just going to write E sub A because we know that's what that is over here. By lowering the energy of activation for a reaction. But how do they do that? How do they just lower the energy of activation and say, haha, graph, now you're like this? They don't just wave a magic wand and poof, there's less energy that's required to go into this reaction. They actually do something. So I want you to leave a little bit of space here. We will fill in the blank here. Enzymes work by lowering the energy of activation for a reaction by doing something. All right, we're going to fill that in a little later. I got to show you how that works. So let's go back to orange. Why not? Let's take a look at our, again, generic substance A reacts with substance B to form product C plus D, and enzyme Q is the enzyme for that. All right, let me see. Let's do some different colors here. Let's say that substance A is actually shaped like this triangle, and that substance B is shaped like this green ball. Enzyme Q, on the other hand, let's go for some, like a reddish color here. Enzyme Q is a globular protein, and I'm going to draw it like this. Here is our enzyme Q. Have I made it obvious enough what I'm going to do here? I hope. This should look to you like a little kid puzzle. You know, those wooden puzzles where a kid has a star shape and they have to put the star shape into the star-shaped hole, that sort of thing. Hopefully it is very obvious that this triangle here is going to go in there and that this green ball for substance B is going to go in there. But before I do that, I want to make sure that you are aware that the shape of this site here, this whole area here, is called the active site. The active site is what that spot on an enzyme is called. Active site. If you need more time to write this down, go ahead and pause the video because I'm going to go and erase that right now. Oops, need to erase those babies too. But let's go ahead and put in substance A in here. Triangle. Drawn a little bit bigger so we can actually see this. And I'll put substance B, our green ball, right in there. Now we give substance A and B a new name. We call them substrates. Substrates. And substrates are just reactants, in this case substance A and substance B, that bind to the active site of an enzyme. So substrates are reactants that bind to an enzyme's active site. So here we go. And what it did is it actually is holding them in place so that they can physically react with each other. And it's holding them in the right orientation. The enzyme is holding A and B steady so that it can help them chemically react. And maybe what they do is maybe the two get connected. I'll connect A and B right here. And maybe B gets broken in half. So that when that's done, when these get spit out, this here is going to look like a triangle, this gray-blue triangle, bound to half of a green ball. And this here is going to look like the other half of the green ball. And ooh, maybe this substance right here is actually substance C. And maybe this other half of the green ball over here is actually substance D. Ooh, it actually looks like kind of like the letter D. It's almost like I planned this ahead of time. I planned it this way, you know. But once that enzyme spits those back out, now the products have been formed. Can you see that the enzyme is going to go back to looking like this? There's our enzyme Q. It looks the same at the end of this as it did at the beginning. So how do enzymes work? Well, they lower the energy of activation, but how the hell do they do that? How the heck do they do that? Enzymes work by lowering the energy of activation for a reaction by binding to substrates at their active site. They're like the chemistry.com of the cell. They bring reactants together so that they can chemically react and have fun. And think of it this way too. Like if it weren't for chemistry.com, maybe person A and person B would never have met. If it weren't for enzyme Q, substance A and substance B might never get together. So enzymes are kind of the match.com, chemistry.com of the cell. So they work by lowering the energy of activation for reaction by binding to substrates at their active site. And can you imagine if something happened to that active site there, if the site got messed up? Like what if this active site, something happened to this enzyme and its active site ended up looking like this? That does not look like it's going to bind to a triangle and a ball. Not going to happen. And we'll talk about that next time, what happens when enzymes lose their shape and how they lose their shape. Before we go, I do want to mention just one more little tidbit about enzymes. And that's how we name them. You know how glucose C6H12O6 is a carb, simple sugar, and the names of sugars almost always end in ose, glucose, lactose, for example, is another sugar. The names of enzymes have a similar ending. Names of enzymes almost always end in ace. They end in ace. So they end in ace, and another thing about them is that we try to name them after the substrate that binds to them. So often named for the substrates that bind to them. So for example, if the substrate, let me erase this over here. Let's get rid of glucose. Substrate over here. If the substrate is lactose, the enzyme that binds to lactose at its active site is called lactase. Lactase. This gives us an idea of what the enzyme lactase does. Well, it binds to lactose and it helps break down lactose. So people who are lactose intolerant, people who have a true lactose intolerance and can't digest lactose in dairy products, oftentimes what can alleviate that, unless we're talking a milk allergy, this is not the same thing as a milk allergy, but you can take those pills that contain lactase. Like I think the brand name for that stuff is called Lactaid or something like that. Lactaid contains lactase. Similarly, if anybody here has a dog or a cat and that dog or cat has ever peed on the carpet, you know that that smells really badly, so you better clean that up, right? Well, that's because pet urine, well, anybody's urine, contains a substance called urea in it. And as urea sits out in the air, it oxidizes to some really smelly stuff. So one thing you can do if your puppy pees on the carpet or your cat pees on the rug, oh, cat pee smells really awful, you spray it with this special stuff that's like some sort of enzymatic cleaner. The enzyme that is in those cleaners, like I think I use like something called Natural Wonder, I don't know, but it contains an enzyme called urease. Urease breaks down the urea so that it doesn't turn to those smelly byproducts from sitting out in the air. So we try to name the name of the enzyme after the substrate, and it ends usually in ACE. ACE. There are a couple of enzymes out there that I can think of that don't end in ACE, but they are definitely the exception rather than the rule. So if you see something that has an ACE on the end of it, you know it's an enzyme. If it's OS, you know that it's a sugar, for example. So something like, let's do another one. Sucrose is a sugar that is broken down by an enzyme called sucrase. That's because sucrose binds to sucrase's active site. So just that little tidbit right there is kind of the last word on enzymes for today. So I hope you have a great week, and I will see you next week. Please be watching Moodle as usual. Please be watching your email, but I'm posting things for you on the week-to-week basis on Moodle, making it prominent for you. And next week I will have most likely a homework assignment for you there, and we'll talk about it then. I'll give you at least a week to work on your homework assignment once I assign it. So you'll be good. Don't panic at all, and have a great weekend. And we'll be back next week. Take it easy.